So I've fired these up just so we can get a quick look at what's going on here. So uh, I'm running here with 1,000,000 particles. You'll notice that this is actually more than 1,000,000. That's just because we're having to use multiple of eights. And you can see that it's absolutely hammering my machine at the moment as well. So I will turn these off in a second. Just want you to see drawings more or less equivalent. Texture buffer update is really slow here, and this is a serious bottleneck. But update is very quick compared to the update speed here of about 1,000 or so quicker. It goes between the two. But I'm going to stop these because these are hogging all the resources on my machine. But you can see at the moment we've got a fairly quick update here. It's just this is a downside. And actually that was part of my design flaw when I was building this to start with, which I'll talk on more for the next demo. So same as before, we've got our grid class, and this time the grid is using the vec3x8 class that I was talking about in the previous video. And what I've done is now, instead of using structures of arrays, I'm using array structure with NGL vec3s. I'm using NGL vec3x8. So I've got position and direction. So if you can sort of think that this is now going to encompass 8 positions each time. Every time I do some maths on those, it's going to use 8 of them at a time. I've also got some acceleration structures here. So again, I'm using the M256 values here. So my acceleration, float array of 8 accelerations and speeds. Now, there are 2 parts to this. There are the parts of this where we're working in SIMD mode, and there are parts of this where we have to fall out of SIMD mode to access the individual lanes or channels within the SIMD register to do something. So when we start up, first thing we're going to do, so you'll see here that I'm allocating a big chunk of data for my position and my direction buffer, and that's going to be m multiplied by 8. So the number of particles that are passed in, I've got this little function which will round to the nearest multiple of 8, and then I divide that by 8, so that I'm basically, if we had a non-multiple of 8, we'd have to have 2 code paths, one to deal with things directly in SIMD and things to do with the leftover individual ones. So I'm just making the code simpler, rounding everything to 8s. And drawing's the same, processes as before. Where it gets difficult now is all of this different elements of the data. So what I'm going to do is I'm going to start with the simple setting of the particles, which is a function. Where is my function to set the particles? So my init grid function is there. Let's go init grid reset particle. So here's my reset particle function. So init grid will loop through everything in the grid and do the particles. So first thing I've got here is a couple of lambdas. So this is random 256. What this is going to do is create a random plus or minus range value, and it's going to store 8 of them in a float, and then that's going to load that into a SIMD register and return it, so that I can fill all the lanes of the SIMD register with a random value. And there's a positive version of it as well, exactly the same thing, but you can see that I'm loading those values in there. And now I'm saying that X, Y, and Z are 3 of these random values. So basically what I'm doing is, instead of setting a single position, I'm setting 8 positions in my vec3x8. And again, this is my initial design of this was, well, I'm using a vec3, I might as well just use SIMD to do it this way. As I say, this is a mistake because accessing this data later becomes a real pain, and it is the bottleneck for my code, as you will see. So I'm setting the x's, the y's, and then I'm setting these values through there. I'm setting the y values to 0 there. And I'm doing the same for my direction vectors and setting that. And then I'm filling in my max speed and my max acceleration. So every time I go through now, I'm generating a SIMD value of 8 particles. And my update still threaded. The threaded works nicely. So threaded works with SIMD as it does with everything else. So update particle. So the first thing, I'm creating an array of zeros there, just so that I can set my vec 3x8 for my acceleration. So it's the acceleration vector, and I'm multiplying my direction vector by that, and I'm multiplying it by dt. All of these are the overloaded operators within the SIMD vec 3x8 class here, so I've got operators to multiply by a scalar and so on. So that code is expressed nicely, and it's has as I had it before. I'm then clamping that to the max speed. Again, that's clamping all 8 lanes to the max speed, and then I'm adding that register onto it. So again, the code is exactly the same as I had previously, which is great. Nice and easy to do. Next, I'm checking to see if I need a reset. Now, this is where things become slightly more complex, because with SIMD registers, obviously we've got 8 floats in there. Now, we can do comparison operators, but what that does is it produces a mask, and that mask is basically for each lane going to have a value to indicate whether it's true or false, whether the comparison was true or false. So what I'm doing here first is I'm doing a comparison. So this is saying compare a pack single, so that's basically the 8 floats, of max speed by 0, and then this flag is saying compare less than or equal ordered signaling, which is just whether or not it causes a signal in it. And then that returns a mask value, that returns a value which we can then convert into a mask, which is basically an integer value. So if the mask is 0, it means basically nothing's been set to true, so we can just return. So we don't need to reset anything. So all I'm doing here is checking my max speeds. That's the case, don't have to do anything, return. If everything is set to all true, so if all the flags are true, then I can just call reset particle on all the particles. It's unlikely that this code path will ever exist, but depending on our simulations, it might happen. So I've put it in there, but it's unlikely. Now, the most likely case is that 1 or 2 of the particles' speed have got to 0, and we need to reset them. Now, if we had AVX512, we could actually use this new move mask operation, which would allow us to mask copy a new set of values across, which would be quick. Fortunately, this CPU doesn't support that, so I can't do it. So in this case, what I'm having to do is generate all of the individual values. Again, this is the bottleneck, really. Well, it's not the biggest bottleneck, but this is a bottleneck in the code. So I'm grabbing the X, the Z values for my X's and my directions, and I'm storing those into these new arrays here. Then I'm creating a new array for speed and acceleration and storing those values there. So basically I'm getting the current value for all 8 of the particles. Now I'm creating a bit set. Again, this could be done most probably more efficiently, but bit set works quickly for this, so it's fine. And I'm looping through each of those and saying, is that lane set? Does it need updating? If it does, generate a new value for that particular value in the register. So if you imagine I've taken all the current particle values, I'm going through saying, does this one need an update? If it does, I set that new value. And finally, I load back those values into that register that I'd stored. And yeah, this is quite slow. And actually, this is a process that I have to also do for checking the bounds. So when I'm checking the bounds to see whether I've hit any of the other objects, I'm doing a similar sort of thing. I'm extracting my X values, my Z values, and my speed. Then I'm going through and I'm comparing the current particle positions with the edges. And if it's not a 0 value, that means that one of them is hit. So I will bomb out early if that's not set. Otherwise, go through, find the ones that hit, recalculate the new dot product reflection value. I've hard coded it in here, and then reset the register. and then I do that against the 4 walls that are there. And again, that's fairly slow. But our biggest bottleneck through all of this is actually the drawing routine. And the reason this is slow is because every frame I need to loop through and grab my texture buffer value. So what I'm doing here is I've got this function called fill array. And what fill array does is being passed in a an array of 8 vec3s, it extracts the X, Y, and Z values from the registers and then loads it into that vec3. And then what I'm doing is I'm adding that into this buffer that I've created there, and I am actually mapping the position buffer in my OpenGL space. So basically I'm saying, you know, that texel buffer I created, map that into my client address space, and then looping through and refilling in chunks each one of those. Now the reason is I'm having to do this is because I've got my array of these vec3 by 8s, and this data is not contiguous in memory like it would be for anything else. So I've got to unpack that data. That's a seriously slow bottleneck, and it's, as you can see, when I run this demo with a big chunk of data, you begin to see that this is not particularly efficient or particularly useful. So whilst my updates are particularly quick, my texture updates here are not that quick. This is still a lot quicker than any of the other demos. Overall we're getting a pretty good speed here, as you can see, but it's still not the quickest I can do because I've got that update, and that's purely to do with the way I designed this and did the buffer. And thinking in SIMD is a completely different mindset. And in the next one, after going down this rabbit hole, I will show you how I've refactored my code again to get the most efficient version of the lot.